Hi guys, today we'll be studying about Kepler's second law of planetary motion. Kepler's second law of planetary motion. This particular chapter is not there in mathematics, but it's a very interesting application of vector calculus, which is very useful for you to understand that calculus and vectors are not just there to traumatize you in exams, but also it enables us to understand the laws of this universe. And maths actually helps us understand certain concepts in which physics may not enable us to understand that easily. So that's why maths is much better way of understanding some concepts which can be explained numerically. Okay. To understand Kepler's second law of planetary motion, we have to refer back to Kepler's first law. If you remember from my previous video, by the way, the link I will put in the description, the path of a planet in a three-dimensional axis was given like this. Okay, this was the sun in the center. With the sun in the center, the planet traveled in this direction as an ellipse. Okay, when the planet traveled as an ellipse, this was the position vector of the planet, which obviously varied with time. We had a constant vector which is known as c, which was parallel to the z-axis. Okay, and then we had another constant vector which I named in my previous video as c1, which is parallel to the x-axis. Perfect. Let's go ahead and let's draw another shape which is important to us now. If you remember this shape, and we'll go ahead and we'll draw another diagram. This diagram will be only with the xy plane because, as I mentioned before, the planet travels, the path of the planet is in one plane, so it will be the xy plane. This is the y-axis, x-axis, negative x-axis, and negative y-axis. The path of a planet, as mentioned in the previous law, is of an ellipse. Okay, so now, what does the second law says? This is the position of the sun. The second law says that the rate of change of the area swept by the planet is constant. Let me just diagrammatically illustrate this to you. So, for example, the initial position of the planet was here, which is known as R0. Okay? Then the planet, during the course of time, for example, the Earth, in the morning, somewhere here, in the evening, it went somewhere here. A new position is RT. RT. Obviously, when it was sweeping, it covered a particular angle. We can name that angle theta. Okay? And the area swept is A, which is obviously a function of T. What second law of planetary motion says that this rate of change of this area is actually constant. Sorry for that, guys. Okay, so we'll have to prove that. To prove that, I needed to keep in mind what was this vector c. From my previous video, if you guys remember, the vector c was given by c is equal to r into v. Perfect. Now let's say what is r. Since I drew my path and polar coordinates, I'll give my r in polar coordinates also. So in polar coordinates, r will be, this is the magnitude of r, cos theta. The I component will be given by r cos theta, plus the j component. The j component will be given by r sine theta. Okay? Now we have to find the velocity vector. The velocity vector is given by r prime. To find the velocity vector, what we will do is we'll differentiate each component. We'll differentiate the I component separately, and we'll differentiate the j component separately. So here we go. If you look into this, when we differentiate this part, we will use product rule. Product rule says that we'll first differentiate one term, so we'll differentiate the magnitude of r. Keep the other term as it is. Okay? Then we'll add, but I know why we'll subtract. We'll differentiate the second term. Now, if you see the second term, cos theta, usually the differentiation is sine theta, but in this case, the theta is changing with time. So the general law is whenever you see cos of a function, what you do is you differentiate that function, multiply that with the answer of the differentiation. So cos of function, the differentiation will be negative differentiation of that function into sine. So what we will do is here, usually what happens, we have cos of x or cos of theta where they are just single variables. So what we do is when we differentiate that, it will become a 1, and then we just multiply that, so that's not noticeable. So what in this case, since theta is changing with time, we will have here is, we'll keep r as it is, d theta over dt, sorry about that, and then sine theta. The negative sign is because the answer of a differentiation of cos theta is actually negative theta. This will be the I component. Now we need to go ahead and find the j component. The j component will be, again, we'll differentiate the first term, keeping the other term as it is, and then we'll add it with the differentiation of the second term, keeping the first term as it is. And again, we'll follow the same thing because since theta is changing with time, it's a function of time. We don't know what the function of theta is with respect to time, but we know it is a function of time. And then when we differentiate sine theta, it will become d theta over dt into cos theta, and that's our j component. So we have these two particular, we have the value for r and we have the value for v. So now let's go ahead and let's compute the cross product. So guys, you guys noted it down, so I'll just go ahead and I'll do the cross product. Okay, I'll remove this part also. Okay, a cross product is given by I'll use the blue marker because I don't think my black marker is working anymore. R, so it will be here it will be R cos theta, and here it will be so we'll have our j here, right here, and the j components are sine theta, and then for the velocity, the j components are, as I mentioned before, it will be right there, plus r d theta over dt cos theta, and our k components are 0 since the planet is moving only in the xy plane, which means it has only I, j, and k values. So this is a 3x3 matrix. Our vector c is given by the determinant of this 3x3 matrix. So let's find out the determinant, the vector c. The vector c, if you see, we'll first take I, we'll cover the column and the row occupied by I, and we'll take the determinant of the remaining 2 by 2 matrix. So if you do that, we'll cover this first row and the first column. What we'll have is we'll have this as the remaining 2 by 2 matrix, with the determinant of that is zeros. You see, the first element multiplied this one, 0, and then this element multiplied with this element, which is 0. So we'll ignore I. The same goes for j, so negative j. When we cover the second row, second column, and the first row, what happens is the remaining 2 by 2 matrix, the determinant will also be 0. So as you can see, this one multiplied with 0, and this one multiplied with 0. It's a different story when we have k. For the k, when we cover the first row and the third column, we end up with r cos theta multiplied by this value, diagonals will multiply, and then we'll subtract the multiplication of the second diagonal right there. It may seem intimidating at first, but the problem is when you guys actually sit down and solve it and simplify it on your own, it will seem much easier. It's nothing but more algebra at this point. This is the k component. Okay, so the k, I'll write the k here because it's not visible over there. You can write it at the end or at the beginning, it really does not matter. Okay, so the c is given by, if you notice, let's expand the brackets. Let's see what happens when we expand the brackets. It will be r into r prime cos theta sine theta plus, then we will have r square d theta over dt cos squared theta. Okay, then we will have negative minus r into r prime cos theta sine theta and then we will have positive, because negative and negative will be positive, r square d theta over dt, and then we will have sine squared theta. And the whole thing is the k component. It is also proving our fact, as I mentioned in my previous video, that the c vector is completely in a z-axis, is proven by the fact that it does not have any I and j components. It's only having a k component. From this itself, we can notice something. This term and this term are exactly the same and having equal signs. We are left with these two terms. So let's write them down. C is equal to r square d theta over dt cos square theta plus r square d theta over dt sine square theta. Okay. Based on this, I'll continue my simplification. Yes, we can simplify it further. When we simplify this further, how do we do that? We'll take r square d theta over dt as constant. Sorry, as common, and we'll take it outside. We'll be left with cos squared theta plus sine squared theta. This, according to the trigonometric identities, this we all know is 1. So finally we are left with r squared d theta over dt. There you go. Perfect. Okay. But we should not forget that the whole thing is actually right here also. This is a k component. This is a vector. It's a k component. We should not forget that. This is a k component. It's a k vector. Okay. So let's go ahead and let's find the magnitude of c. The magnitude of c, as I mentioned, is it can be divided by simple c. It's given by, because the I component is 0, so 0 squared plus 0 squared plus, we will have the k component squared, r squared d theta over dt whole square. If you simplify this, you will end up with c is equal to r squared d theta over dt, and it's a constant value. Okay, perfect. Now I will keep this in the side so that, because we will need this at the end, c is equal to r squared d theta over dt. Okay, perfect. Now I'll remove everything else. There you go. And let's draw the path again. Okay. An elliptical path with the sun in the origin. Sorry for the bad drawing. We have y, we have x-axis here. This is a polar graph, and this is our initial, and this is our, for example, at the time t, this is the angle. Now, the area, we are concerned with this area, okay? This particular area. I've labeled this area as A of t. So, the angle here is given by, the angle here is actually given by theta naught, and the angle here is theta t. Okay, so what we'll have is we'll have to start from here and end up at here. Okay, perfect. So the area of this graph is given by A of t is given by, if you remember the formula, I'll just remind you, the area of a conic section of a graph, like in the area of a conic section graph, or you can say the area under a polar graph, the area of a polar section of a graph, you say, is theta naught, the initial theta, the final theta, and then what we have here is, there you go, magnitude of r, position vector square, and d theta. So we will deal with this. Let's compute that. So a is equal to, remember a is a function of t, I'm not writing it anywhere down, so I'll just write somewhere underneath so I have enough space. So a is equal to the integration from theta naught to theta, and then we'll have the position vector, the magnitude is given by r squared cos squared theta plus r squared sine squared theta whole square, okay, d theta. The area is given by, then you can further simplify this. If you further simplify this, we'll be left with r squared. Take r squared common, since square and square root will cancel. We'll leave r squared common. We'll have r cos squared theta plus sine squared theta. d theta. Perfect. And now this area can be written as A is equal to, we can simply write it as the integration of from theta initial to final theta r square d theta. So now we will focus on this part specifically, okay? We are in the final stages of deriving our second law of planetary motion. So, if you guys remember, area was given by A is equal to theta initial to theta final r squared d theta. I'll differentiate both the sides with respect to theta, so it will be dA over d theta. Let me just write it down a little bit below so that it does not get overlapped. We have dA over d theta is equal to d. I'll differentiate this part with respect to theta, and then I will get something like this. Okay? So if you do this on your left hand side, you are remaining with dA over d theta. That means change of area with respect to the angle is equal to, and by the way guys, I forgot something. The initial area, it's half here. Why? Because the area of the conic section or a polar graph is given by 1/2 theta naught theta, and then you'll have this right here. This is the formula. Guys, sorry for that previous mistake in the video. Just replace everything with 1/2, 1/2 here too. So you'll be remaining with 1/2 r squared. There'll be no constant of integration because we have limits, okay? Now, but this is a problem. The second law of motion that says that the rate of area swept by the planet, that means when the planet is here, goes here, this rate of sweeping is actually constant. So, I mean, we don't know that. So what we will do is, I will multiply the left-hand side and the right-hand side. I'll remove everything from here. I'll multiply the left and the right-hand side with 1 dA over d theta. I'll multiply it with d theta over dt, so that if you notice, my equation remains constant, and 1/2 r squared d theta over dt. Why I multiplied the left and the right hand side? Because I want to keep it constant. So we'll be left with dA over dt, that means rate of change of sweeping area is actually equal to 1/2 r squared d theta over dt. And from this particular part, we come to know that d theta over dt is actually a constant. This part is represented by c. So we can write that the Kepler's second law of motion is actually true. We'll write it here. So the rate of change of the area, the swept area, so if you see the planet starts from here, it sweeps down there. That rate is actually constant. It is not a variable function. Thank you guys for watching this video. This video will also have the link for the next video and the previous video. The previous video is Kepler's first law of planetary motion, and the next video will actually be Kepler's third law of planetary motion. Thank you guys for watching this. Please subscribe my channel. And if you have any comments, questions, or you want me to do more application-based questions on vectors, because I'll be finishing vectors very soon. You can comment, you can put them down in the comment section, and please let me know how do you like these applications of vectors and calculus. Thank you guys.